Hello, this is Pranvat Singh 20 BC 1645, and the topic of my DA3 presentation is homomorphic encryption. What do we mean by homomorphic encryption? Homomorphic encryption is a pivotal advance in data security, enabling operations on encrypted data without decryption. So basically, in homomorphic encryption, we can perform operations on encrypted data only. We don't have to decrypt it first and then perform operations. So we can or perform operation on encrypted form only. This breakthrough preserves data confidentiality during computations. So data confidentiality is preserved during computations. It provides a secure framework for processing sensitive information also. So homomorphic encryption represents a breakthrough in data security, allowing operations to be performed on encrypted data without a need to decrypt it. This innovation enables partially homomorphic encryption (PHE), supporting either addition or multiplication while keeping data confidential for specific operations. Somewhat homomorphic encryption is another type of homomorphic encryption which expands on PHE. It expands its capabilities by allowing a limited set of both addition and multiplication operations before encountering computational limitation. Fully homomorphic encryption, which is another type of homomorphic encryption, is the most advanced form of homomorphic encryption, which permits unrestricted arithmetic operations on encrypted data, ensuring complete data confidentiality throughout computations. These encryption methods are pivotal in secure data processing, especially in scenarios where privacy is paramount. Privacy is the most is on the top of priority. FHE, that is fully homomorphic encryption, in particular has transformative potential. That is, it enables complex computations on sensitive information while maintaining privacy, heralding a new era in safeguarding data integrity and confidentiality across various computational landscapes. Then we move on to the basics of homomorphic encryption. So, homomorphic encryption allows computations to be carried out on encrypted data without needing to decrypt it first, as we discussed before also. So there are several types: partially homomorphic encryption, which supports either addition or multiplication; somewhat homomorphic encryption, which permits limited operations; and fully homomorphic encryption, which enables unrestricted computations while maintaining data privacy. These methods safeguard sensitive information during processing, offering secure data manipulation without exposing the underlying content, because we don't have to decrypt the data while performing the operations, as we perform operations on the encrypted data only. Then we move on to the types of homomorphic encryption. So there are basically three types of homomorphic encryption. The first one is partially homomorphic encryption. The second one is somewhat homomorphic encryption. And the third one is fully homomorphic encryption. We talk about partially homomorphic encryption first. It supports either addition or multiplication operations on encrypted data while maintaining confidentiality for specific types of operations. For instance, with PHE, we might be able to add or multiply encrypted numbers without decrypting them. So we might be able to add or multiply numbers without even decrypting them, preserving the privacy of data during these specific operations. For example, we take an example of failure encryption, which is based on additive homomorphic encryption, which is partially homomorphic encryption. So we take two numbers C1 and C2, which are encrypted representations of the plain text M1 and M2 respectively. So M1 is encrypted as C1 and M2 is encrypted as C2. So the encrypted sum C1 C2 will decrypt to the sum of M1 and M2 without knowing the individual values of M1 and M2. So we do not decrypt here. For instance, C1 encrypts M1 equals to 5 if initial value of M1 is 5, and C2 encrypts the initial value M2 is equals to 7. So if we compute C1 C2, the encrypted sum, the decryption of the result will yield 5 plus 7 equals to 12 without revealing the values 5 and 7 themselves. Then we move on to somewhat homomorphic encryption. which enhances PHE, the partially homomorphic encryption method. So expanding on PHE, SHE allows a limited number of both addition and multiplication operations before reaching computational limitations. It offers a slightly broader range of computation while still preserving privacy, although it has constraints on the number of operations that can be performed. Here is an example of somewhat homomorphic encryption. So basically, we talk about GSW scheme, which is based on somewhat homomorphic encryption. So in the GSW scheme, we can perform a limited number of additions and multiplications if noise grows too much. Let's consider an example. So as we took previously also, let's say C1 and C2 are encrypted representations of M1 and M2 respectively. And we have encrypted M1 equals to 3, the initial value as C1, and M2 equals to 4, the initial value as C2. So we can perform multiple additions and multiplications on these ciphertexts before the noise reaches a threshold that prevents further meaningful computation. So it is an advanced form of PHE where we can perform a limited number of additions also and multiplication also. For example, we can compute C1 dot C2 plus C1 to get a meaningful result without decrypting. Then we reach on to fully homomorphic encryption, which is the most advanced type of homomorphic encryption, and its third type. So the fully homomorphic encryption enables unrestricted arithmetic operations on encrypted data. So this means you can perform complex computations on encrypted data without any limitations. So there are no limitations in this approach. We can perform complex computations without any limitations on the encrypted data, maintaining the confidentiality of the underlying information throughout the entire computation process. We take example of BFV scheme, which it is a scheme which works based on fully homomorphic encryption. So BFV scheme supports arbitrary computations on encrypted data without any limitations. For example, if C1 and C2, as discussed before also, if they are encrypted representations of M1 and M2 respectively, where C1 has been is encrypted from M1 equals to 6 initially and M2 equals to 9 has been encrypted as C2 initially. So using fully homomorphic encryption, we can perform complex operations such as C1 to the power 2 dot C2 plus C2 minus C1 without needing to decrypt the ciphertext until the final result is obtained. We can later on decrypt when the final result is obtained. It depends on us only. It's our choice only. This result will decrypt to the computation performed on the plain text M1 and M2 without exposing their actual values. So we don't decrypt first. So no actual values of M1 and M2 have been exposed. We compute on the encrypted data only during the computation process. These mathematical examples showcase how each type of homomorphic encryption methods enable computations on encrypted data while maintaining the confidentiality of the underlying plain text because we don't decrypt it. Then we move on to the advantages. What are the advantages of homomorphic encryption? The first one is privacy preservation, where there are for certain aspects in privacy preservation. First one is confidential computation. So homomorphic encryption enables computations on encrypted data, preserving privacy by ensuring sensitive information remains encrypted throughout the entire process. Then another aspect is secure data outsourcing, where homomorphic encryption facilitates secure data analysis in untrusted environments, allowing computations without exposing the raw data. Then another advantage is security enhancement, where there are certain aspects such as protection against breaches. So homomorphic encryption minimizes the risk of data breaches since computations occur on encrypted data. Not on we don't have to decrypt, so it reduces exposure to sensitive information. Then data integrity maintains data integrity during computations, ensuring the results are accurate without compromising the confidentiality of the underlying data. Then another advantage of homomorphic encryption is versatility and utility, where there are certain aspects such as flexible data utilization. So, homomorphic encryption enables data analysis while keeping information encrypted, catering to industries handling sensitive data like healthcare, finance, and government. Then, cloud computing is another aspect where homomorphic encryption facilitates secure computation in cloud environments, enabling organizations to leverage cloud resources without compromising data privacy. Then another advantage is compliance and regulatory alignment, where there are certain aspects such as compliance adherence. So homomorphic encryption helps meet stringent data protection regulations such as GDPR or HIPAA, and by ensuring data remains encrypted during processing, aligning with data with privacy regulations. Then data sharing is another aspect under compliance and regulatory alignment, where the homomorphic encryption facilitates secure sharing of sensitive information, allowing collaboration without exposing confidential data. Another advantage or a field of advantage is innovation and research, where an aspect is advancement in secure computing, where homomorphic encryption helps a lot. It drives advancements in secure computation, enabling innovations in privacy preserving machine learning, data analytics, and confidential computing. Then we move on to the applications of homomorphic encryption. There are few applications of homomorphic encryption that I am going to discuss, such as in the healthcare field, then finance department, then government and law enforcement field, then cloud computing and outsourcing is another application, machine learning and AI is another application, and then lastly, data analytics and research. So, homomorphic encryption has diverse applications across various industries where maintaining data privacy is crucial. So, first one is healthcare, where secure data sharing is enabled by homomorphic encryption by secure sharing of patient data among healthcare providers while preserving patient privacy. Then we talk about medical research. So, homomorphic encryption facilitates collaborative research by allowing analysis on encrypted medical records without exposing sensitive information. Another application is in the finance field, where secure data processing is needed. So, homomorphic encryption allows financial institutions to perform computations on encrypted financial data, safeguarding sensitive customer information during analysis. Then fraud detection is another aspect in the finance department that needs to be taken care of. So homomorphic encryption enables secure analysis of transactional data for fraud detection without revealing individual transaction details. Then another application is in the field of government and law enforcement, where confidential analysis is an important aspect, where homomorphic encryption and facilitates secure analysis of sensitive government data without compromising confidentiality, ensuring compliance with privacy regulations. Then secure cloud usage is another aspect where it allows government entities to leverage cloud services. Uh, it allows government entities to leverage cloud services while keeping classified data encrypted. Then secure cloud usage, cloud computing and outsourcing is another application of homomorphic encryption where secure data outsourcing is needed. So homomorphic encryption enables secure computation on encrypted data in the cloud, ensuring data privacy even in untrusted environments. Then privacy preserving services are also needed. So homomorphic encryption facilitates privacy preserving services such as secure search, computation, and analysis without revealing the underlying data. Another application field of homomorphic encryption is machine learning and AI. So in machine learning and AI, we need privacy preserving AI, where homomorphic encryption enables confidential machine learning by allowing computations on encrypted training data without exposing sensitive information. Then secure model sharing is also needed, where homomorphic encryption facilitates secure sharing of AI models without revealing proprietary data used by model training for model training. So the data used for model training is not revealed because on the encrypted data only operations are performed. Then data analytics and research is the last application of homomorphic encryption we are going to talk about. In data analytics and research, we need confidential data analysis. So it enables analysis on sensitive data sets while keeping the data encrypted, ensuring confidentiality during research and analytics. So research analytics are performed on encrypted data only. We don't decrypt the data. Then collaborative research is also another aspect where homomorphic encryption allows multiple parties to collaborate on research projects without sharing raw data. So raw data is not shared because encrypted data is shared, ensuring data privacy. So homomorphic encryption empowers various sectors to leverage the benefits of data-driven insights while mitigating risks associated with data privacy breaches. Because we work on encrypted data without decrypting, without a need to decrypt it. So its applications span industries where maintaining the confidentiality of sensitive information is critical for compliance, security, and ethical considerations. Now let's move on to the conclusion part. So homomorphic encryption stands allows secure computations on encrypted data, preserving privacy across industries like healthcare, finance, and cloud computing. Its unique feature of enabling full computations on encrypted data distinguishes it from other privacy methods, ensuring data confidentiality even in untrusted environments. As data privacy regulations tighten, homomorphic encryption stands out for its transformative potential in enabling secure collaborations and confidential data analysis while safeguarding sensitive information. Homomorphic encryption stands as a groundbreaking solution, allowing computations on encrypted data without the need for decryption. Its unique ability to preserve data privacy uh, throughout analysis and processing makes it a crucial tool across various industries. From healthcare and finance to government and cloud computing, homomorphic encryption uh, addresses critical concerns surrounding data confidentiality and security. While other privacy preserving methods like differential privacy, secure multi-party computation and secure enclaves offer their own advantages, homomorphic encryption's distinctive feature lies in enabling full computations on encrypted data, ensuring data confidentiality is in untrusted environments. As data privacy regulations become more stringent and the need for secure data analysis grows, homomorphic encryption remains a beacon of innovation, empowering secure collaborations, confidential research, and privacy preserving analytics. Its versatility and unique capabilities make it a transformative force in safeguarding sensitive information while allowing for meaningful data driven insights and computations. Thank you.